in thinking about these things, I want to go back just for a second, back to one of my favorite things, the photoelectron spectroscopy graph. We built the photoelectron spectroscopy graph from the data from the experiment. And over on the right-hand side, we established that that there were these levels where electrons appear in these various atoms. And we have the 1s, the 2s, the 2p, the 3s, the 3p, and the 4s. And that translates into an energy level diagram. So we have the 1s, the 2s, the 2p, the 3s, the 3p, and for now, we'll just stop at the 4s. So for every atom, we're going to put electrons into this energy level diagram consistent with what we saw in the photoelectron spectroscopy. So hydrogen has 1 electron and it's in the 1s. Helium has 2 electrons, they're both in the 1s. And then lithium has 3 electrons in total, 2 in the 1s and 1 in the 2s. Okay, so what we're going to do is we're going to take the energy level diagrams that come from the same thing, from the same information, and we're just going to make sure that we are careful, try to be careful, about the 3 rules that we use for putting electrons in there. And the first rule is called the Aufbau principle. And the Aufbau principle basically says electrons go into the lowest energy orbital available. Electrons go into the lowest energy orbital available. No. Okay. So for hydrogen, it's got 1 electron. In its most stable form, hydrogen is going to put its 1 electron here in the 1s. So for hydrogen, I'm going to draw an electron. And for some reason in chemistry, we draw them with little up arrows and down arrows to represent 2 different parts of the 2 different ways of thinking about the electrons. So this electron in hydrogen, it's in the first energy level, it's in an s orbital, and we're going to draw it with an up arrow to show spin up. Okay? The next element, helium, has a 2nd electron. So if I do 1 electron for hydrogen, when I get to putting helium in there, well, the Aufbau principle says the electron goes into the lowest energy orbital available. Well, in this case, I've got 1 spot down here, and so I'm going to put my 2nd electron down here. Okay, so now I've done helium. Takes care of the first 2 elements. Now, the next rule is the Pauli exclusion principle, and it actually comes into play at this point, even if it seems obvious that we shouldn't need to worry about it. For instance, we know from the photoelectron spectroscopy data that lithium has 2 electrons here and 1 in the 2s, a single electron up here in the 2s. It doesn't have a 3rd electron. And that actually comes partially from, well, it comes from the data, but we are reminded of it by the Pauli exclusion principle, which is the 2nd rule. So the Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers. Do you agree with that, Kevin?
Yes.
Okay, so now the reason this matters in this case is because if I were on my lithium, if I were to, I could violate the Pauli exclusion principle by trying to put a third electron down here in the 1s. But if I put a third electron, it either has to be up or down. And so if I do put it up or down in here, it would have the same 4 quantum numbers as one of the 2 that I've already put in. So the Pauli exclusion principle is just a reminder, don't only put 2 electrons in each orbital. We do it so routinely that we almost never run into problems if somebody tried to put a third one into any particular orbital, because it's so fundamental. But nonetheless, so because we violate the Pauli exclusion principle and put a third electron down in here because it would have the same quantum numbers, we then have to put it in the according to the Aufbau principle in the next lowest orbital. And so I'm putting it there. Next element, beryllium. It's got 2 electrons in the 1s, and it's got 2 electrons in the 2s. So Aufbau principle says the electron goes into the lowest orbital available. Well, here it is. There's an orbital here that's available. And Pauli exclusion principle says they can't have the same 2 quantum numbers, or same 4 quantum numbers, and so we have to put it in what seems the easiest way of saying spin down.
So far, the 2 rules we've been using have been making sense. So we use the Pauli Exclusion Act to prevent more than 3 electrons in one orbital, and the Aufbau principle to put the electrons in the right spot. So I wonder when this 3rd rule is going to come in.
Okay, we're almost there. We're almost there. Okay, so we've done Aufbau principle, electrons go in the lowest energy orbital available. Pauli exclusion principle, no 2 electrons can have the same 4 quantum numbers. Okay, so next element. Next element is boron. It's got 2 in the 1s. It's got 2 electrons in the 2s, and it's got this 5th electron up here, and it happens to go in the 2p. Okay, so I'm going to draw a boron, and I put my first 2 in the 1s, my second 2 electrons in the 2s, and almost everybody does it this way, and I don't see any reason why we shouldn't, but it doesn't have to go in here. I'm going to put this electron over here in this left orbital because Aufbau principle says they go into the lowest one available, and so that's all of these have the same energy, so it's got to go in somewhere into this 2p, and there's no violation by trying to put a 3rd electron in there so far, so I'm going to put in my electron right here.
Yeah, okay.
Okay, so that gets us through 5 elements. When we move to the 6th element, that's when the 3rd rule is going to come into place, Hund's rule. Okay, so the next element is carbon. It's got 2 electrons in the 2s. It's got 2 electrons in the 1s. It's got 2 electrons in the 2s, and it's got 2 electrons in the 2p. So Aufbau principle says my electron has got to go somewhere in the 2p. My 6th electron has to go somewhere in the 2p. Pauli exclusion principle says no 2 electrons can have the same 2 quantum numbers. So I guess that would mean that I can't put it pointing up in this orbital, right? Mm-hmm. And then the 3rd rule is Hund's rule, and that becomes useful at this point. It's one of Hund's rules. And Hund's rule says, basically, when available, the electrons go into empty orbitals. So I've got my 6th electron, that carbon electron that I want to put in somewhere. And so I've got a choice between putting it in here in this p orbital that already has 1 electron, or putting it in these 2 over here that are empty. And you can imagine that at the same energy, if I put a negatively charged electron next to a negatively charged electron, they're going to have some repulsion. And so putting that electron in here, in this half occupied orbital, will actually be a little more unfavorable. And so that electron I can put over here. You'll also notice that I put this electron pointing up instead of pointing down. And the reason I've had it pointing up is because there is a little bit of extra stability by having all of these 3 orbitals with the electron spin in the same direction. And so that's actually part of Hund's rule also, that says that when you put electrons into orbitals, if the chances of them interacting with each other are smaller if they all have the same spin. And so as a result, having the same spin amongst the 3 electrons, well, in this case, these 2 electrons, but with the next element, the 3rd electron, they're less likely to encounter each other, which will minimize negative electron-electron repulsions. So as a general way of thinking about it, we put that 6th electron in one of these 2 orbitals, and we have it designated the same direction, the same spin, definitely the same spin as the one that we had already in there. All right, so let's do a couple more, just keep on going here just a little bit. So next element, nitrogen. Nitrogen, two electrons in the 1s, 2 in the 2s, 3 in the 3, or sorry, 3 electrons in the 2p. And so when it comes time to putting that nitrogen electron in here, Oathbow says it goes in the lowest orbital. Pauli exclusion principle says it can't be spin up in either of these 2 orbitals. Hund's rule says it goes into an empty one whenever it gets the opportunity. And as I just tried to explain, we're going to put it in this 3rd p orbital, into this p orbital. Okay.
So far, so good.
Okay. So we could keep on going here. So that was nitrogen, oxygen. Oh, okay. Here now we've got some choices to make, and we'll have to use these rules again. So oxygen apparently has 2 electrons in the 1s. It has 2 electrons in the 2s and 4 electrons in the 2p. So here's 2 electrons, 2 electrons, 1, 2, 3. Now, so according to Oathbow principle, we got to go into the lowest orbital available, lowest energy orbital. That's not the 3s. It's down here in the 2p still. The Pauli exclusion principle says it's got to be it can't be spin up with any of these, because then it would have the same 4 quantum numbers. And Hund's rule says when available, they go into empty orbitals. Well, there aren't any empty orbitals that are available, so I'm going to put it in the most traditional way possible. Spin down in this 2p. Okay, so next electron. According to Oathbow principle, the electron goes in the lowest orbital available. That's one of these 2. According to Pauli exclusion principle, it's going to be, again, have to have it drawn as an arrow facing down, right? Because it's got to have different quantum numbers, and we've got no empty orbitals. So I'm going to go, there's one more, there's not the next element, which would be fluorine, and then here comes neon with 10 electrons. Jumping to sodium, sodium's got one more electron, goes into the lowest orbital. the 3s, to magnesium. Okay, magnesium, oh, we got these nice 3Ps that are just so close, so tempting over here. But no, no, no. They go in, the magnesium's electron goes into the 3s. Now we're at aluminum. Okay, aluminum. If I look at aluminum, it's got 1 electron in the 3p. Then the next element has 2 electrons in the 3p. Then phosphorus has 3, sulfur has 4, chlorine has 5, and argon has 6. And so we just did magnesium, aluminum, silicon, phosphorus. And then now I can do sulfur, chlorine, and argon. And so that, and then the last 2 elements that we've been dealing with are potassium and calcium. So it's very convenient for us that the energy level diagram here matches what we saw from the photoelectron spectroscopy experiment, and we can fill them using these 3 rules: the Aufbau principle, the Pauli exclusion principle, and Hund's rules. And so if you can wrap your heads around them at that point and begin to see where the electrons are, which orbitals the electrons are going to be in, you should be able to handle almost everything that's going to happen in this course regarding energy level diagrams and electron configurations. One of the things that will come up and that you'll see in the text is that we'll go into what happens with beyond the 4s, and you'll see that there are some changes in terms of the energies of the orbitals and how they overlap. But the three principles still apply. Aufbau principle, Pauli exclusion principle, and Hund's rule still apply, even when those energy level diagrams become a little bit more complex.
Yeah, certainly. And you can also use these energy level diagrams for ions, for explaining ion stability, how some elements may prefer one electron configuration over the other. And so just really getting the hang of it can really help you advance your understanding of chemistry.
Yeah. For most of the next 3 or 4 weeks, having your head wrapped well around the energy level diagrams and how what represents stability and what represents instability will really help your understanding.
All right then.
Okay, thank you, Kevin.
Thank you, Dr. Hunter.